Lesson 3!
Distance.
Displacement.
Graphing.
Woo!
Not actually as much fun as we're trying to make it sound like. Why do we graph things, ladies and gentlemen? If I was to try to describe to you that I am on a beach, this beach is on an island, I've got white sand, I've got blue water, I've got this mountain in the background, you could actually start trying to make a mental picture. The only catch is that everybody in this room is going to see something entirely different based on their skills, based on their prior experiences, based on a beach they may have visited. So why would we graph? Well, everybody who looks at data interprets things a little bit differently. But when we graph, everybody sees something the same. So if I show you this picture of this beach, now you're all picturing the exact same beach, and we would all much rather be there than buried in snow in the middle of April like we are in 2018. So, while graphs do require a little bit of work, it's important to note that they're actually a lot better when we want to analyze data. When we want to see what's going on with a very large data set, instead of doing thousands of calculations, make a picture.
So what makes this a good graph? Okay, what makes a good graph? Okay, if we took a look at this wonderful example that we have here, this almost looks like a graph McLeod would draw.
Can we go back up for 1 sec? Because it does say at the end of that, not this graph. This is a terrible, terrible, terrible graph. This is the worst graph we could find.
What makes it bad, McLeod?
Well, for starters, what is this a graph of?
Huh.
There's no title. We have no clue what this graph is about. What else don't you like on this, Rainer?
Well, if we take a look at this side, we have some numbers over on this side, but what do these numbers actually mean? And, not to mention, if we take a look at this scale on the side, it's climbing by a whole bunch of different amounts as we climb up the side. Okay, again, we need to know, if you're going to put a scale on the graph, we need to know what is it of and the proper units associated with that variable.
So they should all be the same size. For example, if 4 to 5 right here is this big, then 2 to 1 should be the exact same size. They've obviously missed by a little bit. What else don't I like? I really don't like that across the bottom we have no clue what these numbers are. We have no clue what they represent.
I don't even think there's numbers there, McLeod.
We don't even have units. There is nothing across the bottom. That is absolute filth.
And you know what else grinds my gears? If we take a look at this, we have 2 different types of points. One's white, one's black. What do they mean? Why is there 2 different sets? Are they all composed? Why are we drawing a line through both sets?
Now, this also looks like a very common type of economic graph where people try to fill in lines between dots. Do you know for sure that right here, at this value, you had exactly this amount? In science, we don't always. We graph all of our points. We don't always know what they're doing. So normally we try to do a line of best fit. This connect the dots. You guys were all really good at this when you were 5. You are no longer 5. You no longer play connect the dots.
Woo! Oh, hold on, go back.
Oh,
The other thing, obviously we have, you can see along the top here, we have a whole bunch of scale points written in here. Right? Again, kind of like the bottom, but nothing's really put there again. So we don't really know what's actually going on here. So, again, do better.
now this, again, just a random graph grabbed from the internet, but this graph is great for all the same reasons the other one is terrible. If we went through the checklist, we know what this is a graph of. If you don't know what resistance is, we don't care. At least we know this is a graph of resistance.
What else is important? As we didn't see on the last graph, we have a axis title on both axes, X and Y, okay, as well as we have equal scales going up the sides. Okay, obviously in between each one of these jumps, there's, looks like 10 lines in between there. Each one is worth 1, and it is consistent all the way up the graph. And same thing on the X axis as well.
Which is awesome. The other thing that we totally forgot to mention, if I pop back to this graph for a second, if you look in the background, man, those dots are really easy to see, but what's their value? When we get to this graph, we can see grid lines.
Grid lines!
You can actually take a point and go across and actually try to figure out what the value of that point is. You don't have to guess.
Now, what else is important here is when we actually take a look at the graph points, okay, we can take a look here, here. When we are putting these points in, they use error circles. Now, obviously, we don't know advanced calculus. We don't know all that kind of fun stuff to actually get the error down to a plus or minus value. So, what we do in Science 10 and in high school is we just draw a random circle around it to incorporate the error within our points. We know we can't measure things perfectly. That's how we represent it.
In university, you measure it, you make boxes, you actually have to have appropriate lengths on them. Guys, for this, make a dot, put a circle around it, make the circle a decent size so that it doesn't look like a big dot, but also don't make it a ridiculous size so that it looks like a big fat donut. That's a good dot. A bad dot would be this, implying that you don't think you've actually hit the point whatsoever, and you need half the graph to compensate. Now, the other thing that they've done in this graph, you'll notice, is that the data points don't all get connected by a line. But if we look at them, as we go to the right, the data points go up. That's the general trend. So what we have done is we've drawn a line of best fit. The data goes right and up, so the line of best fit goes right and up. And you'll notice that it seems fairly split. If dots number 1, 3, and 5 are all above the line, 2, 4, and 6 are all below the line. So it's kind of like an average.
And what you can do if you're looking to count as well, that's a great way to put it. Okay, you just count the number of dots above the line and below and make sure that they're roughly equal. Okay, so again, that's a great way to determine if your line of best fit. If you have all of your points on this side of the line, obviously it's not best fit. You don't have the average. Do better.
You done missed. Now, the other thing that really grinds my gears is this mentality, and I don't know where it comes from, that a line of best fit has to go through 0. That is absolute garbage. If we look at these data points, we drew this line of best fit, it does not go through 0. That is okay.
Draw the trend.
Now, here are your good graphing components so that you can come back and check this later. As we go through all these guys, we're going to do this really quick. We're going to be very brief, but the full descriptions are here. So when you're looking at a title, please just don't use your axes titles. Actually tell us what is going on. The last one was talking about resistance. The axes titles were voltage and amperage. 2 entirely different things, but the title said something else.
Axes titles. What does the data in the graph compare? Okay, obviously your X is along the bottom, your Y is going up and down. X is usually a manipulated variable, and Y is your responding variable. So we reviewed what those were earlier in the course.
We want to have units attached to our axes. If you're going to measure distance, you should tell us the unit that you measured it in. A kilometer and a millimeter are not the same thing. Time. Just like in class. If I told you class was going to last for 88, you have no clue what's going on. It could be 88 seconds, it could be 88 minutes.
Could be 88 hours.
That would be torture.
The scale. A good graph uses at least half of the page. That's half vertically and half horizontally. Again, you do not want a tiny graph because when we start looking at slope, okay, we have to do some calculations. So we want to try to incorporate as much of the graph as possible.
If your graph looks like this on the right, it's too small. It could have been bigger that way. It could have been bigger that way. Play with the scale. I guess I'm going to erase that. We don't really need that long term.
The values on an axis are all the same precision. Okay, so that means the same number of decimal points going up. Obviously, if the measured values in your data table are 2 decimal places, your axes should reflect that.
Kind of like if you're using the same ruler to measure things, the ruler doesn't suddenly get more or less accurate. The ruler stays the same, so the decimal points stay the same. The data points themselves. Normally kind of funny when we mention this, because students will tell us, oh yeah, just put the points on the graph, no problem. Yes, but actually reading your graph and putting the dots in the right spot is apparently a skill. All the way up through Physics 20, Chemistry 30, we see students putting dots in the wrong spots.
And it makes us tear up a little bit.
Yeah, because you take what should have been a very nice, beautiful graph, and all of a sudden we have
And you ruined it!
Frankengraph.
Error circles. Obviously, we talked about this before. Put the dot, draw a little circle around it, done.
Now, the line of best fit. Ladies and gentlemen, you are always fitting the trend of the data. Rather than just studying all of your points, look for what they seem to be doing. 2 examples, very common for Science 10. What trend does the data seem to show there, Mr. Rayner?
Looks kind of like the example we talked about before, a straight line.
Great. Try to draw a straight line. Again, if all the points were up here, you missed. If the points are all kind of close, we're doing pretty good. if we look at our data and our data seems to go like this, what shape does that look like?
Curve!
So I would draw a line of best fit that was a curve. Now, if the line of best fit is this, a straight line, you will use a ruler. It will be awesome. If the line of best fit looks like this, you have to go freehand. Now, do we expect your freehand line of best fit curvature to be 100% perfectly circular, hit every point and be awesome?
No.
Just draw us a half-decent curve that seems to hit some of the points. Don't draw it more than about 4 or 5 times if you are really OCD that it needs to be perfect. Stop. Now, we're going to actually graph some data. We're going to show you the progress, hopefully in terms of steps. Then we're going to try to draw a line of best fit, but we found out the smartboard doesn't let us use a ruler, so our line of best fit is going to be an attempt at a straight line that might not be. After each step in this, though, ladies and gentlemen, if you had graph paper, you could actually be trying this, or trying to predict what's the next thing that should be here. If you can do it all, good for you. If you can't, don't worry. In class tomorrow, we're going to figure it out.
And this is probably my favorite point of the presentation. While setting up a good graph takes time, it's far easier to do it right the first time than to do it again and again and again and again. And again.
I think the record for a student redoing graphs is around 6 times. If they had just done it right the first time, they probably could have saved themselves maybe a half an hour. So if you have no time to do it right, you're going to probably end up doing it at least twice.
Woo!
Now, here's the data set. Ladies and gentlemen, the data set disappears. So, at this point, if you're trying to follow along, maybe not a bad idea. Pause, write this down. We did. So now we can actually see what this looks like on our graph paper. If we look at this, though, we can see right here our manipulated variable came first. Our responding variable came second. Our variable has what will be our axes title. It has a unit, and if you notice, they all have 1 decimal place. They were all the same precision. Same thing on the responding. We have our displacement. It has a unit. Because it's a vector, it has a direction, and we still have every single one with 2 decimal places, even if that means that the last place is a 0.
And with this data table, again, we have a table title describing what this data is representing.
Rainier, you're not allowed to be skateboarding in the halls.
I do what I want.
So, you start out with a sheet of graph paper. Obviously, compared to that graph we saw before, this graph does not have major and minor axis lines. It does not have bold ones every 5 or 10. So, the quick count on this is that we have 40 units going across. We have about 35 units going up. I think it was 30 or 35. Now, if we're looking at this, ladies and gents, we have 40 units going across the bottom. If I have 40 units and I need to show the data up to about 12, I can just do some quick division. Now, the way we normally recommend it is how many units do you have? Or sorry, how much data, what does your data go up to? So if we were looking at this, our data on the x-axis, our manipulated, goes up to 12 divided by the 40 lines. We get a value that is about 0.3. Now that would represent 0.3 seconds for every single line. Now, don't be a fool and try to label every single line. Bulk up to some sort of multiple. So instead of 0.3, we're going to go up to maybe 0.4 or 0.5. In this case, we can see that we have 5 lines getting up to 2. That means each line is actually going to be worth approximately 0.4. Now, the only reason we did this was, instead of going to 5 lines for 2.5, just erase that. Instead of going for 4 or 5 lines going up to 2.5 as if they were a 0.5, we went to just 2 because that actually corresponds to our data, which makes our life a little bit easier. If I move this little guy, you can see in the bottom right, we have actually put the axes title and the unit there. What should we do next?
Obviously, we need to figure out this other axis title. So let's keep rolling through. If we take a look at what we should be doing, we have a total, the total data set that should be going up the top. The highest value is 42. So we'll be going 42 divided by 35, which gives us roughly a climb of 2 units. Okay, 2 units per line.
The actual value is 1.2. Guys, just always round up to make sure that it fits. If you try rounding down, you're going to run out of lines, and that's a bad day.
And again, you want to make sure you're rounding up to the easiest counting number, whether it be 1, 2, 5, 10, 20. You guys get the point.
Now, same idea. Do we want to go through this and label every single line as 2 4, 6, 8, 10, 12, 14. That's a lot of work. Don't do that to yourself. Now, a nice easy number would be 10. Just for the sake of making things different, this time, took it to 8. Only because if you're doing a graph, you're probably going to jump to 10. 8's a slightly harder unit to use, but it's the exact same thing, so we're going to end up still just fine in how we represent our data set. Now, at this point, we have our two axes. They both have titles. They both have units. The only thing we are now missing is in the general setup. We should put a title on this.
Yeah, we should. Whoa!
This is figure 1. Rainier attempting uniform motion on his skateboard in the hall. You'll notice that the table title has now moved over, but instead of it being table 1, it's figure 1 because it's a graph. So, what do we have to do now? Well, this graph looks pretty much ready to go. All it's missing is our data. So, I'm going to read out the points, and we're going to try to graph them. The very first one happens at time 0, displacement 6. The second one, we go to time 2.0. We go to displacement 12.5. Perfect. Is it? Okay, sounds good.
Come on, McLeod.
I'm looking at it from the side.
Give me the next point.
4.0. 18.5. 6.0. 23.5. 8.0, 29.00.
Okay, 24, 6, 8.
10 is at 36. And lastly, 12 is at 42. So it's important to note here, guys, some of these values had 0.5s. But Mr. Rainier drew them in the middle of their set. And then there were ones that didn't have a 0.5. He drew them in the middle of the set. This is why we do the error circle. You can be a little bit off, and it's going to be just fine. So, we've got all of our data. What does it seem like it's doing? It seems like it's going up and to the right. It seems like it's a straight line. So, should we draw a curve? No. We want to draw a straight line. Bear in mind, we don't have the ruler for this. This is going to be free-handed.
Pressure's on. Not bad.
Not bad. It curves a little bit. We notice that some points are above, some points are below. We didn't hit 0 when we hit the axis, but that is okay. That is our line of best fit. Now, the very last thing, why do we have a line of best fit? On the other graph at the beginning, it actually did a slope calculation, but you guys don't need to do resistance, so we're going to do a slope calculation off this one. Now, instead of playing connect the dots and calculating a whole bunch of different little individual components, the line of best fit allows us to make life really easy. We are going to calculate slope once. So Mr. Rainier just marked an X on a very convenient set of points. The line of best fit goes through an intersection of this line and this line. So we should be able to figure out what the values are exactly. The first one is 1.2. by 10. The second one is 13.2 by 46. Now, it's nice to know here, I don't remember if we did, it's nice to note that the accuracy here, 1 decimal place, 2 decimal places, when Rainier drew his numbers for these new points, he put the same level of accuracy. Now, how do we figure out the slope? Back of your periodic table. I dropped the pen again. On the back of your periodic table, you have a formula. It's called slope.
Whoa, 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 whoa. They're given this formula?
Yes. You do not have to memorize this. In math, if you memorized it, good for you. The formula is rise over run. Sound familiar? Okay. We normally use the form slope is equal to y2 minus y1 over x2 minus x1. This is point number 2. This is point number 1 because it came first. So we would literally just put our values in. The y value of 2 was 46 minus the y value at 1, which was 10. The unit for this side was meters. East. And east. draw on the black space.
Ooh.
x2, 13.20 minus x1, 1.2. Oh, that shouldn't have 0 attached.
Almost as if you have an eraser.
Seconds. I do have an eraser. Look at that. There we go. Okay. Ladies and gentlemen, at this point, get your calculator. Be very careful of your order of operations. We're essentially going to do 36.00 meters east divided by 12 seconds. This works out to 3 meters per second east. Now, what that value actually represents, what a meter per second is the next lesson. Woo! But, ladies and gentlemen, this graphing lesson actually leads to that next lesson. We've been 20 minutes. I think we should wrap it up here. Graphing is going to be a huge skill. If you are ever doing homework in terms of graphing or trying to make a graph, I would highly recommend that you try to do it the intelligent way. The intelligent way is if you don't know what you're doing, open this video up again, watch the actual graphing components, make sure everything is there.
One thing we should quickly talk about. Keep in mind, we have to keep track of significant digits. This should be 3.0 meters per second.
Good call, Mr. Rainer.
That's it, guys. Mr. McLeod's time to sign off.
There is the slope formula for how it works. It's pretty much the exact same as what you used in math and what we're going to use in class, a whole buttload. It's going to be nothing fancy, new, or exciting. Sorry.